So in this video, we're going to talk about the 5-number summary for data and box plots. We're going to spend some time talking about outliers here as well. Okay, so we've seen that Chifaru is a pretty big nerd, and in this case, she's at her grandmother's birthday and she wants to know where her age falls in relation to all the other people's ages at the party. So in this case, there's 20 people at the party. Their ages are as follows: 2, 3, 3, 5, 6, 6, 7, 9, 12, 12, 13, 17, 19. That's where Chifaru is. 23, 24, 27, 32, 51, 68, and 97. So there's 20 people at the party, ranging from very young to very old. Okay, so if we do a quick stem and leaf plot, which I didn't do, but you certainly should, right, this data is skewed very much to the right, so the empirical rule doesn't apply. So how do we say something intelligent about the shape of the data and as well as where Chifaru is in terms of relation to everyone else? So what we do is we use 5 numbers to break the data into 4 even-sized slices. We're going to chop our data into quarters. What we do is we start with the minimum, which is the smallest data value, and Q1, which is the median of the lower half of the data. There's 25% of the data in between these 2 points, between minimum and Q1. Next, we use the median, right? And there's 25% of the data between the Q1 and the median of the data, right? So this is the median of the lower half of the data, and this is the median of the entire data set. We go with Q3, which is the median of the higher half, right? So we take the upper half of the data between the median and the max, find the median of that, and that's Q3. That's our third quartile cut. And we also use the maximum, the largest data value. We'll go through an example on the next slide. All right, so here again is our data. We have 20 data points. So the median is halfway between the 10th and the 11th data point. It's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right, there's going to be our median. Now that we have the median, to get Q1, we take our lower half of the data, this 10, and find its median. So there's 10 data points, so it's going to be between the 5th and the 6th data point. 1, 2, 3, 4, 5. Right? There's our Q1. It's the median of the lower half. Q3 is the median of the upper half. We have 10 data points here. So it's between the 5th and the 6th data point. 1, 2, 3, 4, 5, 6. So Q3 is here, right? Q1, median, Q3. Right, the minimum is the lowest, the maximum is the largest. Okay, so these 5 numbers chop up our data into 4 even-sized bits. There's a quarter of the data in here, right? 25% of the data is in here. 25% or a quarter of the data is in here. 25% of the data is in here. And 25% of the data is in here. Something I'm going to mention in a little bit. 50% of the data is between Q1 and Q3. All right. Now, if we think about the sizes of these things, there's a large number of numbers between Q3 and the maximum, right? This quarter, right, this 4th quarter, it looks really wide compared to the other quartiles. So if there's any outliers, it's probably somewhere in here. So we need some systematic way to quantify how wide we expect each of these quarters to be. To do this intelligently, we use how wide the middle half of the data is to help us, right? So the width between the 1st quartile and the 3rd quartile. We call this difference the inner quartile range, right? So the inner quartile range is simply Q3 minus Q1. to get some gauge as to what counts as an outlier, we use 1.5 times this interquartile range, and we kind of use it as a width around the quartiles, above the third quartile and below the first quartile, and say anything that's above that top or below that bottom is an outlier. More formally, it goes like this. Our upper outlier boundary is 1.5 times the interquartile range above Q3. All right, so we take Q3 and we add 1.5 times the interquartile range, and that's going to be our boundary. Any data point greater than that boundary is defined as an outlier. Similarly, on the lower end, our lower outlier boundary is 1.5 times the interquartile range below Q1, so it's going to be Q1 minus 1.5 times IQR. And any data point less than this is going to be an outlier. So next, let's take a look at what this means for Chief-Aru's party data. So for Chief-Aru's party, the interquartile range goes between Q3 and Q1. All right, Q3 was 25.5, Q1 was 6. 25.5 minus 6 is 19.5. So that's going to be our interquartile range. So our upper boundary for outliers is we take our Q3, right? That's our top of that quartile. Add 1.5 times this 19.5, and I get 54.75. If we look at our data points, there are 2 points that are larger than 54.75. So the 68-year-old and the 97-year-old, right, grandma, and these are the outliers of our data set. On the lower boundary, Q1 was 6. We subtract 1.5 times our interquartile range, and I get negative 23.5. Well, the youngest person at the party was 2 years old. There certainly wasn't anybody with negative ages. I don't even know what that would look like. So there are no outliers on this end. And lastly, the box plot that we generate in SPSS is a visualization of this 5-number summary, right? There's our minimum, that was 2 years old. Our Q1, remember that was 6. Our median is right in the middle of the box plot, and remember that was 12.5. Q3 is at the top of our box, right? That was 25.5. And then we have our outliers out here. This is data point 20. This is 97 years old. This is data point 19, which was 68 years old. And this here is the largest data point that is still in our, that is not an outlier. Okay, so there's, in general, right, there's 25% of the data in here, there's 25% of the data in here, there's 25% of the data in here, and in principle, there's 25% in here if we include the outlier.